Today's lesson is going to be about kinetics, which is the speed at which reactions happen. And this is something that we care about in the real world because we want things to happen quickly. So a lot of times scientists will study reactions to see if there are ways that they can make them occur faster. So first we need to talk about collision theory. This is the idea that in order to react, the molecules need two conditions to be met. They need to have enough energy when they slam into each other. So if they're moving too slowly, meaning at a cold temperature, they're just going to bounce off each other and they won't have enough energy to actually change their bonds. The second thing they need is the correct orientation. They need to be turned the right way and they need to have the correct bonds broken and formed in order to create the new product. So to increase the rate of a reaction, anytime you talk about changing the rate of a reaction, it's helpful if you can also discuss collision theory, because if you can provide more energy to the particles, then more of them will have enough energy to get over the activation energy hill. Same thing with correct orientation. If you can create more collisions, then there's a higher chance that some of those collisions will have the correct orientation. So as you talk about the rate of a reaction, if you're doing an essay question, it's helpful if you can also discuss collision theory. So there's several ways you can increase the rate of a reaction. The first thing is that you can increase the temperature. Increasing the temperature is going to add more energy to the particles, which means more of them will have enough energy to actually have the collision be successful. And a lot of times they call them effective collisions. The next thing you can do is to increase the surface area. And surface area is how many areas of the particle are actually exposed to the surface. So for example, if you have a big cube like this, if we talk about, if we talk about this one cube right here, we have this side exposed, and underneath it is exposed, but the other three sides of this little corner right here are tucked into the cube. And so the molecule can't collide on those other three sides. So only 50% of this cube is available for those collisions. Whereas if I break it off of the cube and I have that little cube like this, then all six sides of it are exposed. And so there's a better chance that they'll have the correct collision. So increasing the surface area, you can also add a catalyst. And I didn't talk about this in our last video, but I probably should have. So a catalyst is going to decrease the activation energy. So if we go back to this energy diagram, remember that activation energy is this amount of energy to go from the reactants to the top of the hill. And if you add a catalyst, it provides a pathway for that reaction to happen where the hill is going to be shorter. So if you start two particles here and you race them, the one that goes over the shorter hill is going to get to the products faster. And so the shorter the activation energy, the faster it's going to happen. Then you could also do some things like stirring it. That's going to provide more collisions, which would hopefully give you more effective collisions as well. And when you watch the Edpuzzle for today, you'll be able to see some of these as well. All right, so the next thing we're going to talk about is equilibrium. We are going to spend so many weeks on this that you are going to know this forwards and backwards, which is kind of a pun in and of itself because that's what equilibrium is. So equilibrium, you hear that word equal in the middle of it. It does not mean that you have equal amounts of particles or equal amounts of reactants and products. It has nothing to do with amounts of stuff. It has to do with the speed of the reaction. So equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. So you're going to have two reactions happening at the same time. For example, if we just do a synthesis reaction, you'll see it written like this, where you're going to have two arrows. The A and B are colliding and forming AB, but at the same time, some of the AB is breaking apart to form the two different particles. And so both of these reactions are happening at the same time. When they happen at the same rate, the numbers will stop changing. So we talk about the data being constant, which does not mean that they're equal. So once a reaction has reached equilibrium, it does not mean you have 50% reactants and 50% products. What it means is that however many reactants and products you have, those numbers are going to stay constant. So maybe you have 10% of this and 90% of this. If the AB is breaking apart as fast as the AB are coming back together, then these two numbers are not going to change. So the way scientists know that they've reached equilibrium is that the numbers stop changing. All right, let's talk about how to calculate equilibrium. There's an equation that we're going to use for this. K is called the equilibrium constant, and you're going to put the products on the top, and you're going to raise them to the power of their coefficients. Let me erase some of this. Okay, so products on top, reactants on the bottom, and you're going to raise both of these to the power of their coefficients. So in the balanced reaction, if it has a coefficient, it's going to become an exponent. If you have more than one reactant, then you're going to multiply them. Do not add them. I see a lot of people stick a little plus sign in there. So you would multiply if you have more than one reactant, or same thing with the products. Two things. One is, for some reason, we tend to read reactions, well, we definitely read reactions left to right, but we tend to read fractions top to bottom, so it's really tempting to put the reactants on the top. For some reason, it's just human nature. So be careful, make sure you have products on the top and the reactants on the bottom. So whatever's on the right of the arrow goes on top, whatever's on the left of the arrow goes on the bottom. And then the second rule is that your coefficients need to become exponents. And the final thing is that if you have solids and liquids, you do not include them. So no solids and liquids. You're only going to include things that are AQ or things that are gases. So if there's a solid, like if AB right here was a solid, you just wouldn't include this in the reaction. Let's do a few of these, or at least one, so you can see what I'm talking about. So let's do this for, we'll just make up a reaction. So if we have 2A plus 3B, and we're turning it into 4C plus 5D. It's called the equilibrium expression. It just means setting up this fraction. So first of all, the C and the D are going to go on the top because they are the products, and you're going to raise them to the power of their coefficients. So 4 and 5. A and B are going to go on the bottom, and this is 2 and this is 3. Then they might give you numbers. So if they gave you, for example, the molarity of each one of these, you would put this in brackets. Brackets indicates concentration. If they gave you the pressures, you could plug them in. So they can give you various information about these, and you just plug them into this fraction, and then you're going to calculate K. And that will give you information about what's going on with the reaction. Because if K is greater than 1, remember K is products over reactants, then it tells you something about this fraction. It tells you that the products are bigger than the reactants. If K is less than 1, then that tells you the bottom of the fraction is bigger. So once we reach equilibrium, we can say that we have more reactants or more of the products. We say it lies on the side of the reactants. And one more thing about K, if you can go ahead and understand that temperature is the only thing that affects K. It's hard to write and talk at the same time. Temperature is the only thing that affects K. And so, and we'll do that more when we do Le Chatelier's principle. And actually, yeah, we're going to save Le Chatelier's principle for another time. We'll do that in a different video. So that's it for today. Go ahead and try the equilibrium setups. You're going to set some of the fractions up, and then on the bottom 3 questions, you're going to actually calculate what K would be. Good luck, and I'll see you in class.